At SAS, we love bold questions, outrageous and impossible questions. The answers are waiting to be discovered because space isn't the new frontier. Data is. And with the right questions and the right analytics, we make data do amazing things. Like make the world safer, faster, healthier, and kinder. All we have to do is ask the data, analyze it, shape it, and make it work smarter for everyone, everywhere. With SAS, you can turn data into answers and ask the questions that move the world forward. SAS, curiosity forever.
Hello everyone, my name is Vuk and I will be your host in two tracks. In the second stream, on the first track, Transforming Healthcare with AI, we will have 4 speakers and welcome to Data Science Conference. Our first speaker will be Amibath Saxena. He is a founder and CEO of Anexus. He is an artificial intelligence, data science, and Lean Six Sigma consultant and trainer with overall 32 years of experience in healthcare, manufacturing, and service domains. He has been involved in mentoring AI-based applications for AI startups. He has trained more than 50,000 professionals worldwide, which includes high-profile staff and ministers from Ministry of Health. His talk for today will be machine learning applications in healthcare, Saudi Arabian hospital case studies. Amitabh will discuss the use cases in Saudi Arabian hospitals and discuss the use of popular machine learning algorithms to create the models which were deployed successfully and are giving satisfactory results. Amitabh pre-record his video and now we will see his talk. Thank you.
Hello everyone at DSC Europe 22. I'm Amitabh Saxena and I'll be speaking on machine learning applications in healthcare. Let me share my screen. So we'll be learning about a little bit of introduction to AI and data science. Then I'll talk about the theory of machine learning and then specifically logistic regression and SVM with some case studies in these two algorithms. About me, I've got 32 years of experience and I also conduct training programs in AI in data science. And I've got around 200 clients all over the world, primarily into Lean Six Sigma. And now as a data scientist, I've been consulting with some of the Ministry of Health in a few countries. About the organization, we have been around for the last 17 years. And we have certified many people and also consulted for many organizations. So now let us look at how technologies are enhancing the healthcare industry and what are the applications of artificial intelligence and machine learning in healthcare. So looking at the applications of artificial intelligence, we have image-based diagnosis like radiology. The AI-based automatic positioning and centering in CT imaging is promising new technique for reducing radiation dose and optimizing imaging workflow and image quality in imaging. It is highly likely that in the future, the creative work of radiologists will be necessary to solve challenging problems and to oversee diagnostic procedures. AI will absolutely become part of their routine in diagnostic or diagnosing basic cases and helping to assist with repetitive jobs. Then we have got in image-based diagnosis, dermatology as well, and ophthalmology, pathology also. Genome sequencing researchers are using deep learning to identify patterns within high-volume genetic datasets. These patterns are then translated to computer models, which may help predict an individual's probability of developing certain diseases or help inform the design of potential therapies. Apart from that, we have ML for biomarkers discovery, clinical outcome prediction, and patient monitoring, inferring data status through wearable devices, autonomous robotic surgery, etc. And some of the other applications are listed also here in the table, like basic biomedical research. We have automated experiments, automated data collection, gene function annotation, prediction of transcription factor binding sites, simulation of molecular dynamics, literature mining, and in traditional research, translational research, we have biomarker discovery, drug target prioritization, drug discovery, drug repurposing, prediction of chemical toxicity, genetic variant annotation, and in clinical practice, we have disease diagnosis, interpretation of patient genomes, treatment selection, automated surgery, patient monitoring, patient risk stratification for primary prevention, etc. Now, many of the advances are made possible by machine learning. Machine learning is the science of giving machines the ability to learn and find insights by processing the data without explicitly programming the machines on what to do. And deep learning is a type of machine learning which is based on an artificial neural network. Supervised machine learning aims at predicting the desired output based on the input data. Supervised machine learning methods work by identifying the input-output correlation in the training phase and by using the identified correlation to predict the correct output of the new cases. So we will see some examples in a short while. In unsupervised machine learning, a type of machine learning, this is a type of machine learning that aims at inferring underlying patterns in unlabeled data. For example, it can find subclusters of the original data, identify the outliers in the data, or produce low-dimensional representations of the data. And in reinforcement learning, we have algorithms which aim at using observations gathered from the interaction with the environment to take actions that would maximize the reward or minimize the risk. Reinforcement learning algorithm, called the agent, continuously learns from the environment in an iterative fashion. So here is some theory and then a case study for logistic regression and support vector machine. So let us begin with the logistic regression first. Logistic regression is one of the most popular machine learning algorithms, which comes under the supervised learning technique. It is used for predicting the categorical dependent variable using a given set of independent variables. So here the outcome is a categorical or discrete value. It can be either yes or no, 0 or 1, true or false, etc. But instead of giving the exact values 0 and 1, it gives the probabilistic values between between 0 and 1. It is much similar to the linear regression with a difference in how they are used. Linear regression is used for solving regression problems, whereas logistic regression is used for solving the classification problems. So instead of fitting a regression line, we fit an S-shaped logistic function which predicts two maximum values, which is two values between 0 and 1. The curve from the logistic function indicates the likelihood of something such as whether the cells are cancerous or not, a person is obese or not based on its data, etc. The sigmoid function is a mathematical function used to map the predicted values to the probabilities. So here we use the concept of threshold value, which defines the probability of either 0 or 1. Values above the threshold values tend to 1, and values below the threshold values tend to 0. Sorry, excuse me. The first case is related to predicting patient mortality from large sets of diagnostic codes in electronic healthcare records using the logistic regression algorithm. National hospital records and official death records for patients with myocardial infarction with a sample size of around 200,000, hip fracture with a sample size of around 170,000, or colorectal cancer surgery with a sample size of around 56,000 were collected. And 1-year mortality was predicted from the patient age, sex, and socioeconomic status, and 202 to 257 international classification of diseases, 10th revision codes recorded in the preceding year or not. That was the binary predictor. So the results were that 1-year mortality was 17.2% after myocardial infarction, 27.2% after hip fracture, and 9.3% after colorectal surgery. Based on the optimism adjusted C statistics for the logistic regression models, it can be concluded that in the large data sets of electronic healthcare records, logistic regression of numerous diagnostics codes predicted patient mortality comparably. Now, let's talk about a case related to SVM. And first, let us talk a little bit of what exactly SVM is. Support vector machine is a supervised machine learning algorithm used for both classification and regression, but it is best suited for classification. The objective of SVM algorithm is to find a hyperplane in an n-dimensional space that distinctly classifies the data points. The dimension of the hyperplane depends on the number of features. If the number of input features is 2, then the hyperplane is just a line. And if the number of input features is 3, then the hyperplane becomes a 2D plane. And it becomes difficult to imagine when the number of features exceeds 3. Kernel trick can be used here. So the SVM kernel is a function that takes low dimensional input space and transforms it into higher dimensional space. That is, it converts non-separable problem to separable problem. So this is mostly useful in non-linear separation problems. Here, kernel does some extremely complex data transformations and then finds out the process to separate the data on the label or outputs defined. So this case is about breast cancer classification. Now, breast cancer is the most common cancer amongst women in the world. It accounts for almost 25% of all cancer cases. It starts when cells in the breast begin to grow out of control. These cells usually form tumors that can be seen via X-ray or felt as lumps in the breast area. Early diagnosis significantly reduces the chances of survival. The key challenges against its detection is how to classify tumors into malignant or benign. Malignant means cancerous and benign means non-cancerous. Research shows that experienced physicians can detect cancer by 79% accuracy, while a 95% and sometimes up to 97% accuracy can be achieved using machine learning techniques. So here is the case. In this case, we need to classify a tumor into malignant or benign, which are one of the attributes. Features are computed from a digitized image of a fine needle aspirate of a breast mass. They describe characteristics of the cell nuclei present in the image. And the 10 real valued features are computed for each cell nucleus. They are radius, texture, parameter, area, smoothness, that is local variation in radius length, compactness, concavity, which is severity of concave portions of the contour, concave points, which is number of concave portions of the contour, and symmetry and fractal dimensions. First, we load the Python libraries and breast cancer data set, and we visualize the relationships between our features. So here is the relationship. And here, 1 or orange indicates benign, that's no cancer, and 0 or blue indicates malignant or cancer. Then we check the correlation between the features, and this suggests that there is a strong correlation between mean radius and mean perimeter, as well as mean area and mean perimeter too. So the data was split here using 80% for training and the remaining 20% for testing. Training data is the subset of our data used to train our model, and testing data is the subset of our data that the model hasn't seen before, and we'll be using this data set to test the performance of our model. SVM model is imported. SVM model was trained using training data set. Why did we choose SVM? Because it has some advantages, like it is effective in high dimensional spaces, still effective in cases where number of dimensions is greater than the number of samples. It uses subset of training points in the decision function called support vectors. So it is very memory efficient also. And it is versatile. So different kernel functions can be specified for the decision functions. Common kernels can be provided, but it is also possible to specify custom kernels. Now, trained model was used to predict the data set. And as we can see, our model this time did not do a good job in its predictions. It is predicted that 48 healthy patients have cancer. We only achieve 34% accuracy in this case. So we need to normalize the training data. So data normalization is a feature scaling process that brings all the values into range 0 to 1. Prediction is done now with scaled data set, and confusion matrix with scaled data is created. And this time our prediction got a lot better with only one false prediction, which is predicted cancer, only one predicted cancer instead of healthy. That means we have achieved 98% accuracy. So to conclude that machine learning has growing applications in healthcare, and many are yet to be explored. Logistic regression can be successfully used in determining mortality rates based on predetermined features, and support vector machines can be successfully used in making clinical decisions based on multiple features as predictors. So with that, I conclude the presentation, and would like to wish best of luck on your machine learning journey. If you have any questions, feel free to ask me. My email ID is given here. It is amitabh@nxs.net, and also a phone, +91 99800 20968, which is having a WhatsApp too. So I'll be happy to respond to your questions. And thanks a lot.